Yeah, thanks for coming. My name is Marco. I work as a data scientist in London, and I'm going to present an introduction to natural language generation. Before we kick off, just want to mention, apart from my job, I also spend time with the local community in London, and I'm one of the organizers of the PyData London conference and meetup. A lot of people know about PyData, but not everybody knows about NumFocus. Maybe you saw me this couple of days, or Stefania, or Robert, or someone else doing the sticker thing at the NumFocus desk. NumFocus is the charity that supports all the open source scientific computing ecosystem, especially for Python. And I just want to mention we have our upcoming conference in London in July. The pound right now is terrible, so it's a good time to visit. If you fancy a trip to London, we can talk about it later. Now on to the topic of the presentation, natural language generation. So the broader topic is natural language processing, so NLP. And in NLP, you have essentially two main pillars: natural language understanding on one side, so going from natural language to a machine representation, and natural language generation on the other side, so from the machine representation to human language. And we have a lot of acronyms, NLP, NLG, NLU, so it's kind of easy to stumble upon it. But we're kind of talking about the same families of algorithms. So specifically for natural language generation, if I give you a brief description of the task, it's about generating natural language, as you might expect, from a machine representation. So this machine representation is going to be crucial. In terms of applications, where is natural language generation useful? I just give you a few examples. For example, summary generation. So let's say you have a big pile of text, too much to read, and you want to generate a short summary with the most important content from the original source. And you can tackle this problem as a natural language generation problem. So reading a big pile of text and generating a short summary with the most interesting stuff. Another example where there was a lot of research, weather report generation, so weather, very British topic. So there was a collaboration between the BBC and some local academic entity to essentially find ways to translate a big pile of data, big table of data, into something that is more human-friendly, user-friendly, if you want. So instead of reading a big table with numbers about temperature, humidity, and whatnot, essentially you could use natural language generation to generate a short description of what's going on. Let's say today a bit raining, tomorrow is going to be a bit more sunny, and whatnot. And the same idea can be applied wherever you have a big table of data, so it's a bit dry to kind of digest from a human point of view, and you can use it to describe the data themselves. Another application is automatic journalism, so generating automatically news articles or articles in the broader sense. And when we say automatic journalism, maybe it's a bit controversial because it sounds like we want to get rid of journalists. Well, in reality, we want to support journalists, just like we use, let's say, spell checkers and whatnot to improve our writing. You could also think about ways to aid the journalists to come up with new articles. Also, in the corner of automatic journalism, there's the big issue with misinformation and fake news, as you probably know them. Well, of course, generating fake news is relatively cheap, and fighting fake news is a bit more expensive. So the idea is, well, if you know how fake news are generated, then you can kind of tackle the problem. So knowing about how to generate language can be also used in the process of mitigating the issue of misinformation. And finally, virtual assistants or chatbots, as they're called nowadays. So Siri, Cortana, the Google Assistant, but also Alexa and many, many other products that introduce a natural language interface, so something that is more natural for a user, talking, asking about stuff, and then getting something in return. And these are already products on the market. They've been around for a few years. Sometimes they work well, sometimes they don't. Sometimes, if you try to talk to Siri, set a timer, or what is the weather like, that's fine. But if you try to chat about philosophy and the meaning of life, sooner or later the chatbot will get stuck in a loop. So this type of technologies, they work well when the domain is well specified, kind of narrow, and the task is clear. So this was just a bit of an overview on potential applications, but basically everything that deals with a natural language can benefit from some natural language generation. So in terms of modeling, how do we get there? We're talking about language modeling, which is something we've been doing now for, as a community for many decades. So language modeling is about building a language model. So the starting point is, what is a language model? It's a model that gives you a probability of a sequence of words. Sequence of words could be a phrase or a sentence or a big chunk of text. So a language model will give you a probability of a sequence. What do we want from the model? We want to capture some aspects of the language. So for example, you would say, I'm going home. You don't say, home I'm going, right? So the order of the words does matter in natural language. And you want the model to capture this aspect of the language. So you would like the probability of I'm going home to be much higher than the probability of home I'm going, that should be kind of close to 0. So word ordering is something you want to capture, and also word choice, something you want to capture. If you think about the Italian word casa, could be translated into home or house. But again, you say I'm going home. You never say I'm going house. So you want the model to capture this probability, so to give you a higher probability for I'm going on compared to I'm going house. So you would like the model to capture this type of aspects. How do we get there? How do we come up with a model then? The starting point is let's start simple. Start with randomness. So there's a thing called the infinite monkey theorem. It's a real thing. The infinite monkey theorem says that if you put a monkey in front of a typewriter, given enough time, infinite time potentially, the monkey will be able to generate the whole work of Shakespeare. The issue is we don't have infinite time, but otherwise the theorem is quite solid. And just for color, about 15 years ago or so, a university from Devon in the southern coast of England, they tried to actually work on the infinite monkey theorem. They put a keyboard in a monkey cage, and they were observing how the monkeys were typing. And it was going well at the beginning. Monkeys were kind of typing and observing on the screen what they were typing. But then eventually the alpha male took over, kind of smashed the keyboard. So, yeah. Anyway, the researchers, they call it a success because now we know that monkeys are not random. So I start with the implementation for the monkey theorem. I'm using a random choice that gives you, given a sequence in input, will give you an item from the sequence with a uniform probability. And I'm using string printable, which is essentially the collection of all characters, letters, numbers, punctuation, to simulate what you could have on a keyboard. And then the function will try to output what the monkey is typing, essentially. And I've run it a couple of times. I've run it many more times that I'm willing to admit. And that's what you see. You don't see any Shakespeare that's purely random, right? So random characters that don't make any sense. There is no particular word. So obviously randomness, because we don't have infinite time, is not going to work. So if you want to do better than randomness, typically we, as a simple baseline, we start from engrams. So what is an engram? It's a sequence of n items given some kind of input, which is typically text, so either a sentence or a single word. So if I want to do some engrams with Python, I typically look into NLTK, which is the Natural Language Toolkit. It's one of the core libraries for natural language applications in Python. Very nice for learning about NLP and whatnot. They implement the function engrams, which takes an input, which is our sequence, and the value for n. So here I'm doing 3, meaning I want sequences of 3 elements. And you need to cast it into a list because engrams per se is a lazy object. So if you want to see the output, you need to cast it into a list. So if you pass the word pizza as a string, and then you want the sequence of 3 elements on the word pizza, you would see the letters P, I, Z, and then it's like a sliding window, I, Z, Z, and then you reach the end. So this one in particular is called a character-based engram, and because we have 3, we call it a trigram, so character-based trigram. Another example could be with a list of words. So let's say you have a sentence, you split it on white spaces, so you will have a list of words, the, quick, brown, fox, as individual strings. You pass the list to Engrams, and you say, this time we say chew as a value for n, and the output is again a sliding window. Start from the left, the quick, that's the first engram, then you slide, quick brown, brown fox, and so on. If you have a longer sentence, you go all the way to the end. This one is slightly different from the other one because we are dealing with full words, so we call it word-based engram, and specifically when you have chew, we call it bigrams. So bigrams, trigrams, and then 4grams, all the way up to whatever. Google released a pre-trained model of up to 7 grams for kind of general purpose English, if you want to build a spell checker and whatnot. You have a big chunk of data essentially from Google. So Engrams is kind of the basic structure, but how do we go from Engrams to a language model? The idea is that we need a big chunk of text. From the text, you need to find all the engrams, so you can use the engram function, break it down into the individual component, and then you can come up with probabilities. The simplest approach would be to count how many words you see, count how many bigrams you see. So, for example, if you want to come up with a probability of observing brown fox, there would be a conditional probability. What's the probability of fox, given that you saw brown already? And you can basically simply count and normalize it over the count for brown. So that's probably the simplest starting point. You can come up with more fancy ways of defining the probability. This is typically good enough for a start. And if you want to see it in action, you can already do it probably on your mobile phone. So when you're typing on your phone, this is a screenshot of my Gmail on my Android phone. So you're typing on the keyboard, and then typically you see a bunch of suggestions, and the word in the middle is the one with the highest probability. So the system will read what you're writing, and then will suggest the next more likely word. You can do it yourself, as a test. You can start typing an email or a WhatsApp message and see what happens. So you could type in my name, Marco is, and then you can see what's going on. Ideally, I would like to see a description of me or my LinkedIn profile or something like that. You never know what happens. So I gave it a try, and this was the output. So Marco is a good time. Thank you. To get the latest Flash player is required for video playback is unavailable right now because this video is not sure. If you have a great day. So what's going on here? You see how locally it's kind of fluent. You have the right sequence of noun, word, articles, conjunctions, and whatnot. So locally, the grammar is okay, but then on a global level, it doesn't make any sense. So probably, if they're using some kind of engram-based technology, they don't go for a big window. They go for a local type of window, and that's kind of the issue with engram. So you have local consistency, but you don't have any any global consistency, any global coherence. And that's what happens. So it's readable. Locally it makes sense, but then when you read the whole paragraph, there is no particular meaning. So the big limitation of language models as we've been doing language models for many years, is the computational cost of using the full history. So computing the probability of a word, given everything that you saw before, is too expensive. So what people typically do, they just use a shorter window. So maybe you can do 3 grams, 4 grams, 5 grams, something like that is more feasible, something you can compute. But then again, you capture local context only, you lack the global context. Anyway, language models are still very useful because they are simple to understand, simple to implement. You can debug them, you can see where the probabilities are coming from, what's going on with the individual probabilities. So they still have a lot of value. For example, for spell checkers, for query suggestion. Very, very useful. Anyway, fast forward, there are more recent, more kind of efficient, effective type of models. So we can look into neural networks. Now, sometimes in the PyData track, the assumption is that everybody knows about neural networks because that's what we always talk about. But I'll just give you a 2-minute introduction in case somebody is new, just to clarify the terminology. So neural networks are a broad family of machine learning approaches where you can define your network as basically connections between nodes. You have nodes and edges, structured in layers. Input and output layers are typically defined by your problem. And then the task for you as the architect of the network is to come up with a structure, excuse me, the internal structure, the number of hidden layers, the number of nodes, and so on. What's going on inside a single node, or a neuron, as we call it. So the guy on the right is the neuron we're focusing on right now. It has 2 inputs in this example. Each connection has a particular weight, so weighted input. And what the neuron is doing is taking all the inputs and do a weighted sum, and throw this weighted sum into a particular function. The choice of function, well, you have many options here, potentially anything, any kind of function. In practice, we typically end up focusing on a specific family of functions because they know they tend to work well. So you want to capture maybe nonlinear relationships and whatnot. So there's a family of functions that we typically converge to, but in principle, this could be any function. And when we say we're training the network, what happens is that you start randomly, and then you run your inputs to the network with the purpose of minimizing some kind of error. This error, we also call it a loss function, so you want to minimize the loss. Sometimes you look at it the other way around, so you want to maximize some other functions. We call it a gain function, or generically objective function. So you have some function to optimize, and that's the purpose of training. And the idea is that with random weights initially, you will get a bigger error. Then you use the error to adjust the weights. So you work your way back into the network using gradient descent, some flavor of gradient descent, backpropagation to adjust the weights. And then the error will drop, basically will go down. And again, in terms of terminology, something you need to consider when you are architecting your network is the size of the batch, so how many data points you're passing every time, the number of iterations, how many epochs. So let's say if you have a data set of 1,000 data points, you can choose your batch size of 100, meaning you will need 10 iterations to complete a full run of the data set, and we call this 1 epoch. You can run as many epochs as you like, and as we're going to see, there's some consideration on the number of epochs that you want to work with. So there is one limitation in what we call vanilla neural networks, also called feed-forward neural networks. Basically, the size of the input and the size of the output has to be fixed beforehand. But text is a sequence, and you don't really know the size of the sequence beforehand. So for this reason, you need a specific architecture that can deal with sequential data. Recurrent neural networks, or RNN, are a family of neural networks that can deal with sequential data. Excuse me. So the limitation here is that we don't have a fixed size for input and output. FF and N is how we call vanilla neural networks, feed-forward neural networks. So when we don't have fixed size, we look into recurrent neural networks that are often described as like a neural network stuck in a for loop. So the block in the middle, labeled as A, is either a node or a chunk of nodes, a sub-component of the network, and you see how this is stuck in a for loop. If you unroll the network, maybe it's more clear because why we're working with sequential data. So every input in the previous times will affect the output at the corresponding time, but also the future outputs. So you can capture aspects of the language. So So whenever you have sequential data, language, time series, and whatnot, you can look into recurrent neural networks. Now, as a family of algorithms, they also have limitations. In particular, there's a problem that is called vanishing gradient. Gradient as in gradient descent. So vanishing gradient means that as you're training, at some point the gradient will become so small that the contribution is basically useless. And the way people describe it is that the network cannot remember what happened long ago. So you have this complex architecture to track sequences, but then the network itself does not remember what happened long before. So you kind of lose meaning here. So some smart guy came up with an extension or a specialization of RNN, which is called long short-term memory, or LSTM in short, and still a recurrent neural network type of approach, but then when you kind of zoom in, it looks a bit complicated. So there are some components inside the recurrent neural networks that are called the gates, and you can use these gates to basically decide how far you want to remember or to forget and so on. And I'm not going too much into the low-level details here, the maths behind it. The first time you look into it, it looks a bit intimidating. There's a huge page on Wikipedia. But then again, it's quite reassuring that you can still define such a complex model with a relatively small set of equations. So 4 or 5 equations basically allow you to define such a complex model. This is a snippet from the Wikipedia page, which is quite huge. And it includes also some suggestions on what kind of functions you may want to use and whatnot. So I'm not going to give you too many details. I prefer to look into the practical side of how to do it in Python. So we're talking about the broader topic of deep learning here. Typically, when we do machine learning in general, scikit-learn would be our go-to library. They do have some support for neural networks, but there is not so much in terms of defining your own custom architecture. Okay, so probably for this reason, in the past few years, we've seen many frameworks, specialized frameworks, coming up: Theorem, PyTorch, TensorFlow, and probably many more. And the one that I mentioned here is Keras. So Keras, as a library, was born as an R&D type of library, so for fast prototyping. It's built on top of some other backend, typically TensorFlow or Theorem, but also the Microsoft Cognitive Toolkit. So it uses one of those libraries as backend, and it will hide away all the complexity from the user. So the idea with Keras is that you have a very simple high-level API. It runs easily on a GPU, so here I could write my own code. It runs on a CPU, and then I could push it on AWS or whatever kind of cloud system with a GPU support, and the same code will run seamlessly. And in my opinion, it's simply just easier to start with. The ecosystem per se is moving quite fast, so things are going to change. For example, the author of Keras, the original author of Keras, now works for Google. Google develops TensorFlow, so TensorFlow and Keras, probably eventually they're going to be one thing. They're already one project. One of the two basically will incorporate the other. So let me give you the LSTM example. So what you need to do with Keras, you need to start with some kind of network definition. So we have a sequential model, and we need to add some layers. And the nice thing about Keras is that they implement already the LSTM type of layer, which simply asks you to define how many nodes you want and the type of shape for the input. Here, I'm defining a model for a character-based network. So it will read the characters individually. Len chars is basically the size of the vocabulary, the number of different characters. And then to close the network, you basically introduce a dense layer where everything is fully connected. I'm choosing some numbers here just as kind of a starting point, and I'm choosing softmax as a function, again, as a starting point. There are a few options. We kind of know that if it's not softmax, is going to be ReLU or sigmoid, one of those guys. You need to do some configuration. You need a flavor of gradient descent for the optimizer. RMS prop is one of the latest implementation for the optimizer. LR is short for learning rate, which is the step that you take for the learning process. And the way I'm defining the network and the task itself, you see I'm using categorical cross-entropy. If you've done some classification, maybe that's what you use as well for classification. So the task that I'm defining is kind of rephrased as a classification task. So given some kind of piece of text, the task is making the classification of the most likely next character. So this is what's happening with this configuration. And then the training process, that's the usual fit type of interface. It takes additional inputs for the batch size, for the epochs. Here I'm using 60 epochs, just to say, a big number. And with the callbacks system, you can also print out, make it more verbose, and print out what's going on epoch by epoch. So you can follow the training of the network and see how the training kind of evolves. After fitting, you want to serialize your model. You want to save it. So the fitting can take, days, potentially, if you have a big data set. And then you want to save the model and use it for predictions. The predictions will be in real time. But the important part is to save the model. You can do pickle typically in Python, but for Keras specifically, because of some low-level detail in TensorFlow, pickle wouldn't work. It will raise some kind of exceptions, so you need to use the particular save method. This will save in HTF5 format. So we have our model trained. How do you generate new text? So it will take some kind of seed text in input, and then it will make a classification for the next character, and simply making a sampling over the potential characters. Some details are missing here, but that's the overall idea. So the input of the prediction is the seed text, and then it will give you some kind of output. What I'm showcasing here now is basically a generation of random text that sounds like Shakespeare. So I have a big data set of work by Shakespeare, again from the infinite monkey idea. And I want to see if my neural network can come up with a new Shakespeare-like poem. So the part that I underline is the seed text. So I take some random snippet from Shakespeare, so that's real Shakespeare. And I try to see if there is some sense in what the network is coming up with. So after one epoch, after the network has seen the whole data set, it doesn't look like Shakespeare. You see how it's basically a sequence of, you have a sequence of random characters, some punctuation, some spaces, so it doesn't look good. I let it be for a while, so after about 5 epochs, things are changing, still random, still gibberish. But you see how the morphology is kind of getting in shape. So you have words of a number of characters that kind of look like a real language, but then when you look specifically into the choice of characters, there is no particular meaning. You see also how the punctuation is kind of in the right place. You have comma and the space, and then a next word. So, better than before, but still far from real language. I let it be for a while. After more than 20 epochs, still too random, so nothing happens. So what's going on here? Well, probably there's some issue with the structure of the network. So what people typically do is what is called tuning. So you need to go back to your network and do some change. Do we need more layers? Do we need bigger layers with more nodes? Or the other way around, we have too many nodes? Do we need more data? Probably combination of everything. So here the process sounds a bit like a try and error. So you need to find some configuration that works well. So long story short, I did some tuning. I came up with a more complex structure where I have, I think, 4 LSTM layers, but then everything else was basically the same. And you see how with just after one epoch, still far from proper language, but it looks already much better than before. So you have words that are potentially of the right size, you have the punctuation in the right place, and so on. I let it be for a while. and after 20-ish epochs, that's what I get. So, sounds like Shakespeare. And yeah, if you read it, it's a bit intellectual. Some of the words are not real. But if you think about it, well, Shakespeare himself invented a lot of words. So the network is basically replicating the work of Shakespeare. So yeah, that's how far I got. Just wrapping up, a couple of tips for the process. Now, you will need a GPU. This type of models are computationally very expensive. To give you a flavor, I ran a first example on my laptop. It took about 90 minutes, 1 hour and a half. I pushed the same code on AWS, the cheapest GPU machine, took only 4 minutes, so 22 times faster. So that's how it is. So what I do typically, I develop locally with a tiny data set just to make sure that the pipeline, the wiring is correct, it works end-to-end, and then I push it on the cloud. In terms of data, you will need at least 1 million characters. That's the total size of the data set, at least 1 million characters. The Shakespeare data set is roughly 4 million characters. And typically, people agree that you need to let it be for at least 20 epochs before you see something interesting. And remember to save your model. So I told you twice, so now you know what happened. Summary is a fun game. So generating random Shakespeare is not a real task, but there are potentially many applications. There's always a bit of discussion to have between dealing with simple models versus complex models. So the suggestion is start simple and then add complexity later. And if you're interested in neural networks, Keras is kind of the starting point, and it will make your life easy. So that's all for me. I don't know if you have a couple of minutes for questions. Otherwise, you can find me at the non-focus desk later. And yeah, thank you very much.
Thank you a lot, Marco. We have time for questions, if there are any questions.
Couple over there.
Over there, okay.
Hi, thanks for your talk. I actually have 2 questions.
Yeah.
The first one is whether did you ever need to go more low level instead of using Keras, maybe because you have to tune the architecture or use something more particular that Keras doesn't provide, so going more low level, for example, using PyTorch or TensorFlow? Did you ever need to go that low level?
The need is a real need, not really. I had a look at it, and my favorite option is still Keras. I prefer to look at things from a distance because it still gives you all the configuration options that you need. So for tuning the network and customizing things, that's good enough for me. I don't do research in neural networks per se. I'm just kind of a user, so that's good enough for me. I would say a lot of people get into TensorFlow. TensorFlow has a lot of support from Google, so it's more probably famous or popular if you want. But for me, I prefer to stay high level. Give it a try, that's my suggestion.
Okay, and the second question is, with regards to the number of epochs to choose, if compared to other applications of neural networks that may, how can I say, overfit the data set, in this kind of area in neural language generation, could a high number of epochs lead to overfitting, so lead the neural network to some sort just copy-paste some sentences of the input data set?
So it's always a risk overfitting. Excuse me, but you're still sampling over a probability distribution. So it's quite rare to observe, because we're going character by character, to observe a literal copy and paste. So you might see kind of a short sequence that is a copy and paste. Typically, it's kind of smart enough to avoid this sort of issue. But overfitting in the broader sense is always potentially an issue. The number of epochs I mentioned is a rule of thumb. It's what people kind of observe empirically, but it's not, written on stone.
Okay, we have time for another one. Please don't put the faster.
There are some type of pre-processing of the text. for the training. For
So in
training the
terms of
model.
pre-processing, if you go with a character-based model, there's no particular pre-processing to make because the input will be a sequence of individual characters. If you want to choose a word-based model, then the pre-processing is basically tokenization, splitting the input into a sequence. The pros and cons, I would say character-based models will capture morphology of the language. English is not a very morphologically rich language, but if you're dealing with, let's say, Italian or Spanish, it's more morphologically rich than English. If you're dealing with Finnish, it's more morphologically rich than Italian and Spanish. If you're doing a kind of query suggestion type of thing, you have short, relatively short text, so you might want to look into word-based models. There are options, essentially. Yeah.
Okay, last one, very quickly. Okay, so who was the... okay.
I'll talk in private.
Okay.
Somebody here?
Thank you. Thank you for the talk. In the process of trial and error while tuning the number of layers, did you find some empirical correlations between properties of the text, like morphological is present or not, and the best number of layers? That I mean, I'm not saying something.
Yeah, no, it's
rigorous.
it's a good question, but long story short, I'm working with English mainly. So I never thought about it. There are a couple of papers that talk about machine translation and the way this type of models compares across languages that you could look into. There's one from Facebook and probably many more. But I never, honestly, never dug into the multi-language context, at least with neural networks. Thank you.
Okay, thank you a lot, Marco. We will find it like 4 meters from here.
Outside the door.
So
With
thank you,
with
everyone.
stickers.
Yeah, with stickers.